In the previous section, we focused mostly on ions and ionic compounds. We learned that an ionic compound exists wherever a positively charged cation and a negatively charged anion attract each other. Ionic compounds are always made up of ions. They could have a 1-to-1 ratio of cation and anion, or they could have a different ratio as long as the positive and negative charges cancel each other out. The attraction between a cation and an anion is what's called an ionic bond. Ionic bonds are simply an electrostatic attraction between opposite charges. In this section, we'll focus more on a different type of compound. These compounds can be called covalent compounds, although occasionally you'll also hear them referred to as molecular compounds. The term covalent gets its name from the word valence. Covalent compounds are compounds that form from shared valence electrons. So there's some major differences on a molecular level between ionic and covalent compounds. The first is with what they're made of. Covalent compounds are made of neutral atoms. So unlike ionic compounds, which require the individual entities involved to be charged, covalent compounds can exist between any neutral atom and a second neutral atom. This means there's a much more diverse group of covalent compounds because they can involve virtually any element on the periodic table. The covalent bond itself is also very different than the ionic bond. Instead of opposite charges attracting, as is in the case of an ionic bond, a covalent bond, because it's between two atoms, is more complex. It involves the sharing of electrons. So why would an atom share electrons with another atom? Why wouldn't it just always form an ionic bond? Well, the answer really is the same fundamental basis. Ions form so that an atom can become more stable than its neutral state. Another way an atom can become more stable is just to share electrons in order to get its full valence shell. Let's take a very simple example. The hydrogen atom, as we've seen all quarter, is the simplest atom on the periodic table, and it has exactly one electron. That one electron is a valence electron, and we know that hydrogen, in order to be stable, would like to be isoelectronic with a noble gas. So it could lose one electron, or it could gain one electron to fill its S subshell. Now, if it loses one electron, it becomes a hydrogen ion. But another option for this hydrogen atom is to find a second hydrogen atom that also needs one more electron. When these two hydrogen atoms get into close proximity with each other, their valence shells can overlap. When their shells overlap, each hydrogen has access to two electrons. It doesn't absolutely have or own each of those electrons, but it has access to both of them. So the hydrogen on the left has two electrons that are moving close to its nucleus, so it is now stable. The hydrogen on the right also has two electrons moving close to its nucleus, so it's more stable than the neutral hydrogen atom. This is a perfect example of a covalent bond. It comes from having shared electrons. This is the simplest covalent bond because there are two electrons being shared, and it's what we call a single bond. If you wanted to draw this molecule, we could draw it by writing a hydrogen and a second hydrogen and drawing a single line between them. That single line symbolizes these two electrons, and it's called a single bond. Not all atoms are as simple as hydrogen, but remember, the fundamental basis which drives all of the different reactions, all the different bonding in the chemical world is just the octet rule. Atoms are trying to be most stable, or they are at their most stable, when they have access to 8 valence electrons. We just saw hydrogen only needs access to 2 because, as we talked about, that's one of the exceptions. It only has an S subshell, so it only needs 2 in order to be stable. But let's look at an example of a more complex atom that would need access to 8 valence electrons to obtain its most stable state. Let's look at nitrogen. When you find nitrogen on your periodic table, its atomic number is 7. We can draw its electron line diagram and its electron configuration, and we'll see right away that its 2p subshell has 3 electrons in it. So each one of those 2p orbitals is still missing 1 electron. Now nitrogen, being in group 5, is one of the elements that does not frequently form ions on its own. It doesn't become a cation or an anion easily. But if we think about the arrangement of nitrogen, it has a paired set of electrons in its 2s subshell, and it has 3 single electrons in each of its 2p orbitals. If it would like to, or if it wants to become more stable, it can find other electrons to share so that it can fill those holes in its 2p subshell. Again, another simple option is always to share electrons with something like hydrogen. Hydrogen has 1 valence electron and is looking for 1 more to share. If we bring a hydrogen into close proximity with that nitrogen, that allows the nitrogen access to the hydrogen's electron. Let's look at how that affects its line diagram. Now that the nitrogen is in close proximity to that hydrogen, we've essentially given it 1 more electron in that line diagram. Now it only has 2 missing electrons, or 2 unfilled orbitals. All we have to do to complete that electron line diagram is bring it in close proximity with 2 more hydrogens. So there's a second hydrogen, which brings 1 more electron, which again adds 1 more electron into this line diagram. And finally, to complete the line diagram and make nitrogen as stable as possible, if we bring a third hydrogen into close proximity with it, we now have a complete line diagram. The nitrogen now has access to 8 electrons, and each of the hydrogens has access to 2 electrons. So the hydrogens are in their most stable state, and the nitrogen is also in a very stable state. If we wanted to draw this molecule, there's a little more to consider, and we'd be drawing something called a Lewis structure, which we'll talk about in a few minutes. As you can see, the nitrogen is able to bond with the hydrogen, and it's only one of the options for nitrogen.
All covalent bonds involve electrons being shared between atoms, but there can actually be quite a bit of variety in exactly how the electrons are shared. For instance, different covalent bonds can share different numbers of electrons. The simplest covalent bond is what's called a single covalent bond, more commonly just referred to as a single bond. A single bond, as we saw previously, is represented by drawing a line on a piece of paper. That line connects 2 atoms together, and it represents those 2 atoms sharing exactly 2 electrons. In addition to single bonds, it's also possible to have double and triple covalent bonds. Double covalent bonds, which are represented by drawing 2 lines between 2 atoms, represent what happens when those atoms share 4 electrons. So drawing 2 lines on paper represents the sharing of 4 electrons in a double bond. And finally, the triple covalent bond, or just triple bond, represents the sharing of a total of 6 electrons between atoms. These bonds differ not only in the number of electrons that are shared, but also in how closely they bind the atoms together. As you might guess, the triple bond with its 6 shared electrons brings these 2 atoms very close together. As a result, the triple bond is both the strongest and the shortest covalent bond. It brings the atoms as close together as possible, and it also binds them together. It would take the most energy to break a triple bond. On the other side of the spectrum, the single bond is a relatively weak and longer bond compared to double or triple bonds. The double bond in the middle is stronger than the single and weaker than the triple bond.
When we draw a covalent molecule, one of the most common ways to draw it is through something called a Lewis structure. A Lewis structure is just a specialized type of drawing that gives 3 important pieces of information about a molecule. The first piece of information is that this structure will show all of the atoms that are involved. So we always expressly draw out each atom that is in a molecule when we do a Lewis structure. The second part of the Lewis structure is we draw all of the bonds in the molecule. That means whether the bonds are single, double, or triple, we draw that information into the depiction. And the third one, and probably the trickiest thing to realize its importance, is that we draw what are called the unshared or the lone electron pairs. These are the electrons that are not involved in covalent bonding. Often they're the electrons that were already part of an atom before it started bonding. Even though it may not seem important right now to draw these electrons in, they're going to have a significant impact on how that molecule reacts because of the shape of the molecule. So make sure we always include the unshared electron pairs, and we'll see why that's important later on in this chapter. To draw Lewis structures, there's a lot of different ways to draw them. I'm going to show you a 6-step process. These 6 steps are not always all needed, so you might be able to skip over 1 or 2 or even 3 of these steps, but make sure that you always go in order when doing Lewis structures. If you go out of order, you may end up with an incorrect structure. For our first example, let's draw the Lewis structure for carbon tetrachloride. Its chemical formula is CCl4. If you'd like to have a printout of these rules so that you don't have to write them all down, I've provided one on our objectives page. The first step in figuring out the Lewis structure for a molecule is to count the total number of valence electrons in that molecule. In carbon tetrachloride, CCl4, I have 1 carbon atom and 4 chlorine atoms. If we remember that the valence electrons for each atom is the same as its group number, this will be a very easy process. I find carbon on my periodic table, and carbon is in group 4. So for my carbon atom, I'm going to add 4 electrons, and then when I find chlorine, chlorine is located in group 7. There are 4 chlorine atoms, so I'm going to multiply it times 4. So I have 4 electrons coming from carbon and 7 times 4 electrons coming from chlorine. So 4 plus 7 times 4, which is 28, gives me a grand total of 32 valence electrons. This number is what we'll call our tally. It's our tally of how many electrons are going to be distributed throughout this entire molecule. Now I'm ready to start drawing the molecule. The first thing to do when you put your pen to your paper is to choose what your central atom is going to be. The central atom in most molecules is the atom that is in the most need of electrons. One way to think about this molecule is carbon has 4 valence electrons, so to reach its perfect octet, it needs 4 more. Chlorine has 7 valence electrons, so to reach a perfect octet, it only needs 1 more. For that reason, carbon is going to be our central atom. So I'll write carbon in the middle of this space. 9 times out of 10, your central atom is the first atom in the molecule. But there are exceptions to that, notably things like acids, because hydrogen is a very poor central atom. So we've chosen carbon as our central atom. I'm going to draw that in the middle of the page, and now what I'm going to do is bond all the other atoms, all the non-central atoms around it. You just need to spread them out. We'll talk about exactly where they should go later on in this chapter, but for now I'm just going to spread them around this carbon, sort of like I'm making spokes on a wheel. So I've just put down 4 chlorine atoms because that's what else I have in this molecule, a carbon in the middle and 4 chlorine atoms. Now I'm going to connect each of those chlorine atoms to the central carbon using a single bond. Remember that a single bond is just a simple line, and that line represents 2 electrons. Here's where we have to make our first adjustment to our tally. Each line that I just drew represents 2 shared electrons. So I no longer have 32 electrons that I can put wherever I need in this molecule. I've used some of those up. I've just drawn 4 lines, and each line represents 2 electrons. So I need to subtract 8 from my 32 valence electron tally. When I do that, I'm going to erase my 32, or if you want, you can just do the subtraction right out on the side of your paper. And I'm going to take 32 and subtract 2, 4, 6, 8 valence electrons. So now I'm down to a tally of 24 electrons. In other words, I've just used up 8 electrons just gluing this molecule together. Now that I've done that, I need to distribute the remaining 24 electrons. The first thing I'm going to do is distribute electron pairs to my outer atoms. Remember that electrons are most stable when they're paired up, so we usually draw them in pairs in a Lewis structure. Let's start with this chlorine atom. This chlorine atom, right now, as it's drawn, has access to 2 electrons. Like most of the atoms on the periodic table, it's most stable if it has access to 8 valence electrons. So it already has 2, it needs 8, so I'm going to draw in 6 electrons, or 6 dots around the chlorine to show that it now has access to a total of 8 valence electrons. Notice that I draw the dots paired up, and usually we think of the atom itself as being a box, and you draw them around 3 or however many sides of the box you need. So I've just drawn in an additional 6 electrons, and because of that, I need to subtract those 6 electrons from my tally. So I no longer have 24 electrons left. I now have 24 minus 6, or a total of 18 electrons. And I'm going to continue doing this for each of my non-central atoms. Now I'll work my way down to my second chlorine atom. It currently has access to 2 electrons through the single bond, so I need to provide it with 6 more electrons in order to complete its octet. When I do that, I've used up 6 more electrons, so I'm going to subtract that from my tally. 18 minus 6 is 12 valence electrons. Now I move on to the next chlorine. At this point, you've probably noticed a trend. This chlorine has access to 2 electrons, so I'm going to provide it with 6 more. And I would subtract that 6 from my tally. The last chlorine is exactly the same. It also has 6 electrons, so I'll subtract that from my tally. And notice at this point, I'm now down to 0 valence electrons. Now I can move on to number 5. If there's any electrons remaining in your tally, those will go on your central atom in pairs, in dots, just the way we did for chlorine. My tally is down to 0 valence electrons now, so I don't have anything to do for step number 5 because I'm already at 0. This is an example of now I get to skip step 5 because it's already taken care of. If I had added any electrons to my central atom, I would then subtract that number from the tally, which should put me at 0. So at this point, you should have 0 electrons left in your tally. The final step in any Lewis structure drawing is to inspect the molecule and determine if every atom has access to 8 valence electrons. The exception to that, there's a few of them, but the main one is hydrogen, which only needs access to 2. So let's inspect this molecule we've drawn and see if any of the atoms needs access to more. If it does, we'll have to use a double or a triple bond in order to get at those electrons. One way to do this is just to move to each atom and ask yourself, does this have access to a complete octet of electrons? As I go to the chlorine here and I look at it, it has access to 2 electrons through the bond, and then 2, 4, 6 electrons on the chlorine. That's a total of 8 electrons. So that chlorine is stable. I go to my next chlorine. Again, it has access to 2 electrons through its single bond, and then 2, 4, 6 more through those electron pairs. So that's a total of 8. It's stable. And I can do the same thing for each of the remaining chlorines, and you'll notice all of them have access to 8 valence electrons, so they're stable. The last atom I need to check is carbon. The carbon has access to 2, 4, 6, 8 electrons because it has a total of 4 single bonds around it. So the carbon has access to 8 electrons. It has a complete octet, so it's stable. Because each of the atoms involved has access to a perfect octet of electrons, this molecule is now complete. This is the Lewis structure for carbon tetrachloride. we didn't need to do any double or triple bonds because all of the atoms were completely satiated and satisfied and had a perfect octet without having to do any more sharing. Let's try another example. Let's do the Lewis structure for carbon dioxide. I promise this one will require some double and triple bonds. So the steps are going to remain the same. Count your total number of valence electrons, choose a central atom, and so on. If you want, pause the video at this point and practice doing this Lewis structure. Okay, are you ready to do carbon dioxide? Let's go. Count the total number of valence electrons. Carbon has 4 valence electrons, oxygen has 6 valence electrons, and because there's 2 oxygens, that gives me a grand total of 4 plus 6 for 16 valence electrons. And again, I get that just from looking at the group number of carbon and the group number of oxygen. I'm going to choose a central atom. Carbon needs 4 more electrons. Oxygen would only need 2 more electrons. And also, carbon is the first element in the chemical formula, so that's a good indication as well that it's going to be in the middle. I'll put the carbon in the middle, I'll put oxygens kind of around the outside, and then I'll connect them together. As soon as I draw those lines, I'm now on step 3. I need to subtract electrons for each line I drew. I drew 2 lines. Each line contains 2 electrons, so I've now decreased my tally from 16, subtracting 2 and 4, so I now am down to 12 for my tally. On step 4, now I get to add electron pairs to my outer atoms. We'll go to this oxygen first. When I go to this oxygen, it currently has access to 2 electrons. It needs a total of 8, so I'm going to draw 6 electrons onto it to give it a full octet. So there's my 6 electrons, and as usual, when I draw something, I need to make sure to adjust my tally. So 12 minus those 6 electrons gives me a tally now of 6. I go to my next oxygen. It already has access to 2 electrons, so I'm going to give it 6 more electrons to bring it up to a perfect octet, and I'm going to adjust my tally from 6 minus 6. I'm now down to 0. At this point, I'm at step 5. If any electrons remain in my tally, add these to the central atom. No, my tally's down to 0, so I don't have to add anything to the central atom. I now have 0 electrons in my tally, and I can move on to step 6. We inspect the molecule we've drawn. If any atom does not have access, now we're going to use a double or triple bond. So you'll notice each oxygen has access to 2 electrons through a single bond, and then has 6 electrons in those electron pairs. Each oxygen has a perfect octet in this molecule as it's drawn. The problem is our carbon atom does not have an octet. The carbon has a single bond on each side, so it has access to 2 electrons on the left and 2 electrons on the right. It has access to a grand total of just 4 electrons. I can't simply draw dots on the carbon or draw electrons on the carbon in order to bring it up to 8 because my tally is down to 0. So the only way I can redistribute electrons to make the carbon as stable as the oxygens is to share electrons. When I share electrons, I'm going to go to one of those oxygens and I'm going to borrow from it 2 electrons. Let's borrow these 2 electrons. By sharing them into the bond, I allow the oxygen to continue having access to the electrons, but I allow the carbon to now also have access to them. So those 2 electrons are going to move down here, and remember 2 electrons is the same as a single line, so they become part of this bond, which makes it a double bond. When I do that, this is very important, I no longer have those 2 electrons on the oxygen, so I'm going to erase them. I now have a double bond between the oxygen and the carbon. Notice it did not change the number of electrons the oxygen has access to. The oxygen still has access to 4 single dots, meaning 4 electrons in unshared pairs, and now through a double bond it has access to 4 electrons, so it still has access to a total of 8. My carbon now has access to a total of 6 electrons. I still need to improve that, and you could do that two ways. One is to take more electrons from the oxygen on the right, but I think the easier thing, or the thing that's a little more visually appealing, is to take electrons from the one on the left. So when I do that, I'm going to borrow any 2 electrons from that oxygen. I'm going to share it into the bond, creating a double bond, and when I do that, I've used up that pair, so I'm going to take it away. Now when I check, my oxygens each have access to 8 valence electrons, and the carbon also has access to 8 valence electrons, 4 through one double bond, 4 through the other. So this is the complete Lewis structure for carbon dioxide. When you do Lewis structures for polyatomic ions, which remember are molecularly bonded molecules that happen to have a charge, they're really going to be the exact same process that we've just been covering. The only difference is a polyatomic ion is an ion, which means it either has extra electrons or it's lost electrons. That means we'll have to adjust the electron tally based on whatever its charge is. If you have a cation for a polyatomic ion, that means it's positively charged, or in other words, it's lost electrons. If it has a positive charge of 1, it's lost 1 electron, and we'd have to subtract 1 from the valence electron count. If it has a positive 2 charge, it's lost 2 electrons, we'd have to subtract 2 from our valence electron count. The opposite is true for anions. Because anions are negatively charged, they essentially have picked up extra electrons. So after you get your valence electron tally, your valence electron count for your Lewis structure, you'll add the number of electrons that the charge indicates. So if it has a -1 charge, you'll add an extra electron to the tally. If it has a -2 charge, you'll add an extra 2 extra electrons. For example, if we were to tally up the valence electrons in PO4 3-, that's the phosphate anion, and I would handle it the same way we've been handling those tallies in the last 2 examples. I'd look at phosphorus, and I find that phosphorus is in group number 5, so it has 5 valence electrons. Oxygen is in group number 6, so it has 6 valence electrons, and there's 4 of them. So that gives me a total of 5 plus 24 is 29, but because its charge is 3-, that means I have 3 extra electrons. So I'm going to add to the 29 3 electrons, and that gives me a total of 32 valence electrons. A lot of times if you forget this rule, you'll notice that you get an odd number when you do your valence electron count, and odd numbers are difficult to work with in Lewis structures. They often indicate something called a radical molecule, and those are a little bit beyond the realm of this class, so most likely if you run into an odd number, you've either added something incorrectly or forgot to adjust for the charge. Now there are some exceptions to the octet rule. The most notable exception, and the one that we've already seen repeatedly, is hydrogen and helium. Hydrogen and helium, because their first shell only contains an S subshell, are completely stable when they have access to 2 electrons. So helium has 2 electrons to begin with, and that's why it's as stable as the noble gases and is counted as a noble gas, even though it doesn't have 8 valence electrons. Hydrogen has 1 valence electron, so as we saw in chapter 4, it can lose that electron, and that's one way for it to become more stable, or as we've seen in this chapter, it can share an additional electron, which allows it to have access to 2. So hydrogen and helium are stable as long as they have access to 2 electrons. Another exception is group 3. Group 3, which consists of boron, aluminum, gallium, and so on, often is completely stable without access to 8 valence electrons. For reasons we don't have time to go into, many of the elements in this group exist in compounds where they only have access to 6 valence electrons. So if you happen to be having dinner with a Nobel Prize winning chemist and that chemist shows you a picture or a structure of his or her latest creation, please don't tell the Nobel Prize winning chemist that it's incorrect because boron only has access to 6 valence electrons. In this case, it's one of the exceptions. Boron, aluminum, gallium all can have access to 6 electrons and be stable, but there's another major exception on the periodic table, and it's the elements that have a d subshell. In certain situations, these elements are capable to do what's called an expanded octet. Sometimes it's called a hypervalent octet. What that means is that the element has actually used its unfilled d subshell to stow away additional electrons. In other words, it can have access to more than 8 valence electrons and still be very stable. There are many different electrons on the periodic table atoms on the periodic table that this could apply to, but don't assume it will occur. The ones that are most common, and you'll probably see even in biology classes, are cases where something like phosphorus or sulfur or chlorine has access to more than 8. Sometimes phosphorus is very stable when it has access to 10 or even 12 valence electrons. So don't be alarmed if you see these molecules in Lewis structures with larger or smaller numbers than 8 valence electrons, but don't assume they'll occur. For our purposes in our class, always get everything to 8 valence electrons with the exception of hydrogen or helium. If you're going into any setting where you're likely to see them in other arrangements, either hypervalent or with 6 valence electrons, you'll cover that in specific examples. So don't worry about it in our class. Now that we know how to draw the Lewis structure for a molecular compound, let's look in some detail about how we can determine the shape of that molecular compound. One way to do this is by using valence shell electron pair repulsion theory, better known as VSEPR theory for short. VSEPR theory simply predicts the shape around a central atom, and it does this, like the name implies, by looking at the repulsion of electrons in the molecule. Electrons, because they're negatively charged, repel each other when they're in close proximity, and they repel each other regardless of what they're doing in the atom. Think about it this way. So far we've been drawing our bonds, or covalent bonds, through lines. A single bond is represented by a single line. When we draw that line, we know it represents 2 shared electrons, but we also know that it's not a totally accurate depiction of what's really happening in the molecule. We know electrons are moving very, very quickly, so it's not possible that those electrons are truly standing still in that line. Because of that, one way to think about those electrons is to draw them as part of a charge cloud. In other words, it's an area of negatively charged electrons that are moving between the 2 atoms. Any bond can be called a charge cloud, whether it's a single bond, double bond, or triple bond. So when we use VSEPR theory, we'll be counting a single bond as 1 charge cloud, a double bond as 1 charge cloud, and even triple bonds as just 1 charge cloud. The other type of charge cloud we'll be encountering is an electron pair. Anytime you see an electron pair on a central atom, remember that looks like 2 dots written next to each other, that will also count as 1 charge cloud. Now these charge clouds, because they contain electrons, naturally repel each other. So if I had 2 charge clouds on a molecule, such as this, right away you probably think that that looks a little odd. And one of the reasons for that is that when I look at that molecule, I know that each one of these charge clouds contains negatively charged electrons. So if those negatively charged electrons are repelling each other or pushing away from each other, why would these 2 bonds be in the position they are? It just doesn't look right. And that's exactly what VSEPR theory is going to tell us. Because these electrons repel each other, 2 bonds located on a central atom won't be at this type of an angle that you're seeing now. Instead, they'll be as far apart as possible. This premise is the basis for VSEPR theory. We look at the central atom, we look at the charge clouds on that central atom, and we arrange them so they're as far apart as possible. When we do that, we get a series of different shapes which have specific names and bond angles that chemists use to refer to them. Let's look at those shapes. The one we're looking at right now is the simplest of the VSEPR theory shapes. It just consists of having 2 bonds going in opposite directions. And again, the reason is that allows the bonds and the electrons in the bonds to be as far apart as possible. So when I look at the central atom in a Lewis structure, I won't see the charge clouds. What I'll see are just single lines. And I can count the charge clouds on the central atom like this. Here's my central atom, and I see that there's one charge cloud to the left and one charge cloud to the right. So I have a total of 2 charge clouds. Whenever you find 2 charge clouds on your molecule, the name of this geometry, or the name of this shape, is linear. So this molecule has linear geometry, and as you probably remember from a math class, when something is linear, it has 180 degrees between the two ends. So the bond angle between that bond and this bond is 180 degrees. This is the linear geometry through VSEPR theory, and it's the simplest one you're likely to encounter. If we have more bonds, of course we're going to have different geometries on our central atom. Let's consider a central atom that has 3 charge clouds. And the simplest kind we can have for that is one that has 3 bonds. So here's my central atom, and let's put 3 different bonds on it. Notice, in order to put these bonds as far apart as possible, I get a shape that probably reminds you a little bit of a triangle. There are a total of 3 charge clouds, 1, 2, 3, and those 3 charge clouds are in a geometry that's called planar triangular. In other words, planar meaning flat and triangle. It looks like a triangle. So the geometry for this is planar triangular. Now the angle between these different bonds, any 2 that you pick, is 120 degrees. So anytime you see 3 charge clouds that are all bonds, you have planar triangular geometry. In other words, it looks like a flat triangle. There's one other way you might have 3 charge clouds in a molecule, and that's if you have an electron pair on your central atom. In some Lewis structures, you're likely to see a central atom that has 2 bonds and an electron pair on the central atom. Notice the way we count charge clouds, this still counts as 1 charge cloud, 2 charge clouds, and the electron pair is a 3rd charge cloud. So on this structure, I still have 3 charge clouds, but this no longer looks like a flat triangle. In fact, if we look carefully at it, one way to think about it is that it quite literally just looks like a stick that we have bent. And that's exactly what we're going to call this geometry. This is called the bent geometry. The bond angle is very close to planar triangular, but the electron pair actually repels slightly more than a bond itself would, and for that reason this usually pushes the bond angle between the 2 atoms to smaller than 120 degrees. It'll still be close to 120 degrees, but we would predict it to be a little smaller. So 3 charge clouds could be planar triangular or could be bent geometry. It depends on whether you have 3 bonds or 2 bonds. The most complex of the VSEPR theory shapes that we'll be doing in this course arrives when you have 4 charge clouds. So on your central atom, in order to fit 4 charge clouds as far apart as possible, you might think about a square, but a square is a 2-dimensional shape. In 3 dimensions, the furthest apart we can get our 4 different bonds is really what looks essentially like a camera tripod. So it's a camera tripod with something sticking up off the top. You have one leg of the tripod coming towards you, one leg kind of going in the plane of this paper, and one going away from you, and then one sticking up off the top. This type of geometry arrives when you have 4 charge clouds that are all bonds. We call this tetrahedral geometry. Tetra usually means 4. So here's 4 charge clouds, 4 bonds, and the easiest way to remember it is it really looks a lot like a camera tripod with a camera on top. The bond angle between these bonds is roughly 109.5 degrees. Notice that's an improvement on if we had tried to draw this as a square. A square would have the angle of 90 degrees between the bonds, and a 109.5 degree bond angle allows the bonds to be further apart. Now, just like we saw with the trigonal planar, it's also possible to have 4 charge clouds that are not all bonds. So one other possibility is if you can imagine plucking off the top of that tetrahedral shape and replacing it with 2 electrons. That would be an electron pair. You still have 4 charge clouds. 1, 2, 3, 4. But now my geometry is different. The way that this looks is kind of like a pyramid with nothing on top. So we call this pyramidal geometry. And just like we saw on the previous example, when you change out a bond for an electron pair, it squishes the molecule a little bit. So the bond angle on pyramidal geometry is usually a little bit under 109.5 degrees. The last shape we're going to look at is what happens when you have 4 charge clouds and you replace another bond with yet another electron pair. So imagine taking this pyramidal shape, plucking one of the legs off of it, and replacing it with another electron pair. When you do that, what you have left is essentially another bent shape. You still have 4 charge clouds. 1, 2, 3, 4. But our geometry now really is just a different version of bent geometry. It's not the same as the one we saw on the previous page because its bond angle is much smaller. Instead of being less than 120 degrees, we're still less than 109.5 degrees. So these are the main VSEPR theory shapes that we'll be covering in this class. 2 charge clouds is linear, 3 charge clouds could be planar triangular or bent, and 4 charge clouds could be tetrahedral, pyramidal, or bent. When you're applying this information, we're going to generally be applying it to Lewis structures. So let's look at the Lewis structures that we've already done in this chapter. Here's our good old friend carbon tetrachloride that we did in our very first Lewis structure a little while ago. When we look at this carbon tetrachloride with all of the lines and all of the electron pairs, remember that all we're concerned with is what is on or touching the central atom. So this carbon is my central atom, and when I look at what's touching it, I can see that I have 1 charge cloud here, another charge cloud here, a 3rd charge cloud here, and finally a 4th charge cloud. So I have a total of 4 charge clouds. My 4 charge clouds indicate my geometry because with 4 charge clouds, all of which are bonds, I know that I can call this tetrahedral. And I would expect the bond angle to be roughly 109.5 degrees. If I really drew this Lewis structure in 3 dimensions, it would be a little tricky, but I might have drawn carbon in the middle and then tried to draw a chlorine coming towards me with my electron pairs, a chlorine going away with the electron pairs, a chlorine to the side with the electron pairs, and finally a chlorine on the top. This is why with Lewis structures we don't usually try to draw in any 3-dimensional information unless it's fairly easy to anticipate. Lewis structures can be any shape you want. It's the VSEPR theory that tells us what shape the molecule will actually have. Let's look at another example. A little while ago we did the Lewis structure for carbon dioxide. When you draw the Lewis structure for carbon dioxide and you count the charge clouds on the central atom, you'll see that our central atom is carbon, and on that central atom I have a total of 1 charge cloud here and a 2nd charge cloud here. So when I look at 2 charge clouds, I know right away that this is what we would call linear geometry. So 2 charge clouds is linear geometry, or the linear shape, and that has a bond angle of approximately 180 degrees. That means if I had drawn the Lewis structure with the correct geometric information, again that's not required, but I would have put the oxygens directly apart from each other to represent truly linear geometry. So that's how we apply VSEPR theory. Once we have a Lewis structure, look only at the central atom, count the charge clouds that touch that central atom, and then determine the shape of the atom in 3-dimensional space. There's one more thing I want to mention about VSEPR theory. Even though we've been using VSEPR theory on relatively simple Lewis structures, it can be applied to very complex molecules, ones that we probably won't run into that much in our class. But think of VSEPR theory as being applied to every central atom, even as those molecules get more complex. Here's an example. What you're looking at is a three-dimensional model of the molecule propane. You probably have heard of propane because it's frequently used for home heating or for heating gas grills. That gas is usually propane. Propane has the chemical formula C3H8. And when we look at the structure for propane, there's not one central atom. There's actually a backbone of 3 carbon atoms, which are each surrounded by hydrogens. So the Lewis structure for propane is really a caterpillar, is one way I've heard it described. It has carbons down the middle surrounded by hydrogen. And if you went and did all of our rules for Lewis structures, you'd see that that really does account for all the electrons and all the atoms are stable. While we might draw it as a straight line, the fact is that each one of those carbons can be treated as its own central atom. Let's look at this carbon on the left. If I count charge clouds for that carbon on the left, I would count 1, 2, 3, and here is a gigantic 4th charge cloud. That's okay. It's still a 4th charge cloud. And we know that when we see 4 charge clouds that are all bonds, that's tetrahedral geometry. That's why in the 3-dimensional version, this carbon atom is not making a straight line, it's making tetrahedral geometry. Let's look at the carbon atom in the middle. In the middle of this structure, if I take away all this information and I look at just that single carbon in the middle, the carbon in the middle has 1 charge cloud, 2 charge clouds, here's a larger 3rd charge cloud, and here's a 4th charge cloud. We see that again the carbon in the middle also has a 4th charge cloud. So that's why in my 3-dimensional drawing I still have tetrahedral geometry. And that's why in 3 dimensions you may notice this shape looks a little bit kinked or bent. That's because the molecule is made up of tetrahedral carbon atoms in the middle. So we have to have a bond angle of 109.5 degrees between all these different bonds. In fact, every atom in this molecule has a bond angle of 109.5 degrees between its closest atoms. The end result is that molecules with a carbon backbone tend to look like kinked or bent lines as you draw them. And in fact, if you continue on to any other level of chemistry, especially a class like Chemistry 122, Organic Chemistry, we'll be running into this because it's one of the ways that chemists draw molecules in shorthand. It's by taking advantage of the fact that carbon always is a kinked or bent part of a line. All I really want you to remember is don't think that VSEPR theory is just for simple molecules. Each atom in a molecule, if it's attached to other atoms, can be classified as having its own VSEPR shape.